we're still doing recursion on trees, and one use of binary trees is an evaluation tree, right? So would everybody agree that this tree represents 3 plus 4 times 7? Do people agree? Anybody not agree? Why don't you agree? Exactly. Exactly. All right, so the point of the tree is to show order of operations, right? All right, so this is again, you evaluate this side and get 7, and this side happens to be 7, that's a coincidence, and then you multiply them and get 49, right? So what's the base case here? It might as well be every node either is an operation, in which case it has 2 children, or it's a number, in which case it has no children. So we don't need to deal with the empty tree, and we can just have that be the base case, right? So, and so now we're going to write a routine that takes one of these trees as inputs, and it takes as values a value for x, y, and z as values, and it evaluates the tree, right? So you might ask yourself, how complicated would this code be, right? You're taking a big tree as input, and the answer is it's really easy. All right, so here's the precondition and postcondition as I talked about. And so then we can ask varied cases, right? So f is our tree, and if f is just a real number, then the answer, like if f is 3, then the answer is 3. And if the answer, if f is just a leaf that has the variable x in it, then we return the value of x and of y and of z, right? If the root is a plus symbol, then we recursively evaluate the left, evaluate the right, add them, and return the answer, right? Similarly, if it's a subtractor, a times, or divide, right? And that's the entire algorithm, right? Does that make sense? All right, so in 2001, you guys have taken 2001 versus my morning class hasn't. So you know all about grammars, right? So this is an expression, right? An expression is a term. A term is a product of factors. A factor is an expression with brackets around it, which is a sum of terms, and so forth, right? You parse tree. Everybody kind of remember that? Right, expression is a sum of terms, right? So what you might not have taken, but I teach periodically because it's my favorite algorithm, is the code for, in fact, you could write, pretty easy to write code that takes as input a grammar like this, and takes as input a tree that's according to that grammar, and builds the parse tree. All right. And in this one, we'll have a routine called Mr. Expression that knows what comes first as a term. So Mr. Expression calls Mr. Term, which builds that whole term up. And then Mr. Expression says, oh, now I have a plus. And he goes and then he calls Mr. Term again, right? So he keeps calling Mr. Term until he doesn't see any more pluses, right? Or maybe minuses. And then he puts all these terms together in a tree with all of these pluses between them, right? Does that make sense? And then you can ask, well, how does Mr. Term do? Well, he does the same, except he calls Mr. Factor and looking for times between them, right? And how does Mr. Factor do? Well, he checks, is it an integer? And if not, he says, does it begin with a bracket? And if it does, then it calls Mr. Expression and then looks for a closing bracket, right? So the input is a string and the output is this tree. And the other times that I've taught this course, the homework assignment was to handle trees and to move about trees. And I gave you the code which started with the string and gave you a tree so that you could easily build trees. But we're not doing that, so it doesn't matter. Everybody good with that? So you all hopefully took calculus at some point in your life because it's very useful and very beautiful. And one thing I do with my non-math friends is I give them some calculus just from drawings and no math whatsoever, right? I taught this course in Africa where all the students had complete degrees in mathematics and knew all the calculus, and they could tell you anything. But I put a curve on the board and said, somebody take the derivative of this, and they just had no intuition about how to eyeball it and get the derivative. So it's good to have some intuition. But that being said, we're now going to write code. Oh, in my first, I don't know if I've ever told you this, my first year teaching, they told me to teach first year computer science, and I gave them such hard things to do. I got them to write this code, which of course killed them. So what does this code do? Is it takes as input a tree like this and differentiates it. So the derivative is actually this, which is kind of ugly. And then you can write other code which takes this derivative and simplifies it. All right, so you might say, how hard is it to write code to take the derivative? And again, it's not very hard. All right, so the input is a tree like this, and the variable that you want to differentiate with respect. And if the function is just the variable x, then what's the derivative of x with respect to x? Right? It's 1. X changes at a rate of 1 as x changes, right? But if f is a constant or y, then we're going to assume the derivative of y with respect to x is 0, right? And then otherwise, remember, we have this tree that we're taking a derivative of, and we don't want to mess with it. We don't want to touch the tree. We want to build a whole new tree that's the derivative, right? So to do that, I'm going to make a copy. Suppose that the function has the root is some operation, right? Then I'm going to copy the left subtree, copy the right subtree. I'm going to differentiate the left. I'm going to differentiate the right. And I do that all recursively, right? And then how do we do our derivatives? Well, what's the derivative of the sum is the sum of the derivatives, right? We took these derivatives and we can just build these trees, right? And then product, what's the derivative of h times g? Well, it's the derivative of g times h plus the derivative of h, derivative of g times h plus g times the derivative of h, if you remember the chain rule, right? So you can just build this little structure and hang these things that we produced off of it, right? And then the derivative of divide is a little harder, remember, because you have this, you're dividing by the h squared. Anyway, that's how we got this tree. Everybody kind of follow that? That's one of the beauties of calculus, is if you know a little recursion, you can take the derivative of anything, right? Taking the integral, of course, is harder. All right, so then this is just way too complicated, and it simplifies to being just this, right? And you can see we have things like times 1, right? So that should be simplified away. So then we wrote this code which would simplify things, and we're making a copy of the simplified thing. All right, so if the function is just a real variable, a variable or a real number, then there's nothing to simplify, so we just return a copy. Otherwise, we recursively simplify the left, recursively simplify the right, and then you just apply all these local rules, right? You know, the rule is you're not allowed to go into the left subtree or the right subtree, but here we're just poking in just a little bit to say, hey, are you the one, right? That's not too looking at a whole tree. It's constant work to say, hey, is my, right? If I'm a times and my left subtree is a 1, then I should get rid of that times and just simplify it to this, right? If my left tree is a 6 and my right tree is a 2, then I should simplify to be 12, right? So here are all these various simplify rules, and if you apply them, just those, you turn that into, right? So into that, right? Everybody good?